Hello there, and welcome to Whispers of Science, where the cosmos gets cozy and wonder takes the scenic route to understanding. Tonight, we're embarking on a gentle journey into one of the most profound mysteries that surrounds us, the shape of the universe itself. It's a question that has puzzled humanity since we first looked up at the stars and wondered what lies beyond the horizon of everything we know. Before we begin drifting through the cosmic architecture, I'd love to know where in the world you're listening from tonight and what constellation might be visible from your window. Right now, fitting, isn't it, here? We are scattered across this pale blue dot, each of us gazing outward from our own unique vantage point, yet all of us contained within the same magnificent cosmic structure. If you find this voyage through space and geometry soothing, intriguing, or simply a peaceful way to let your mind wander, after a long day, I'd be ever so grateful if you gave this video a like and perhaps subscribed it. Helps this quiet corner of curiosity reach others who might need a moment of cosmic perspective too. Now, I do hope this isn't so fascinating that it keeps you wide awake, but if it does, well, at least you'll drift off, knowing something beautiful about the grand theater in which we all perform our small but meaningful parts. So settle in, let your thoughts expand, and let's begin, because somewhere between the curve of space time and the whisper of infinity lies the story of everything. When we speak of the shape of the universe, we're not talking about something you could hold in your hands or sketch on paper. We're venturing into a realm where geometry becomes poetry and mathematics becomes the language of existence itself. The universe, in all its vastness, has a form, a structure that governs how space itself behaves, and that shape determines not just where we've been, but where we're all heading. Imagine for a moment that you're an ant walking on the surface of something vast. You can only see a small patch around your tiny feet, but that surface extends far beyond your perception. It might be flat, like a tabletop, curved like the surface of a balloon, or twisted into something far more complex. The ant, much like us, can only glimpse hints of the greater structure through careful observation and a bit of mathematical detective work. This is precisely our situation as humans trying to understand the cosmos. We're cosmic ants, in a sense, walking on the surface of space-time itself, attempting to deduce the shape of everything from our limited perspective here on Earth. But unlike our hypothetical ant, we have telescopes, mathematics, and centuries of brilliant minds who've given us tools to peer far beyond our immediate surroundings. The question of cosmic shape isn't just academic curiosity. It's fundamentally about our place in the grand scheme of things. If the universe is flat, it suggests one kind of future. If it's curved in a particular way, it implies something entirely different. The geometry of space determines whether the universe will expand forever, gradually slow down, or eventually collapse back in on itself. Like a cosmic inhale following the great exhale we call the Big Bang. To understand why shape matters, we need to think about how space itself can be bent and molded. Most of us grow up thinking of space as empty nothingness, the stage on which matter and energy perform their cosmic dance. But Einstein showed us something far more elegant and strange. Space isn't just a container, it's a participant. It can stretch, compress, curve, and ripple like the surface of a pond disturbed by a falling stone. When we look out at the night sky, we're seeing the universe as it was, not as it is. The light from distant stars and galaxies has traveled for millions or billions of years to reach our eyes, carrying with it information about the cosmic architecture from ages past by studying this ancient light. Cosmologists can map the large scale structure of the universe, trace its evolution, and begin to discern its overall geometry. The cosmic microwave background radiation that permeates all of space is perhaps our most valuable clue. This faint afterglow of the Big Bang carries within it subtle variations, a kind of cosmic fingerprint that reveals the fundamental properties of spacetime itself. When scientists analyze this radiation, they're reading the universe's birth certificate, written in the language of temperature fluctuations and polarization patterns. What they've discovered is remarkable. The universe appears to be remarkably flat, not curved like a sphere or saddle shaped like a horse's back, but geometrically flat. In the technical sense, this doesn't mean the universe is literally flat like a pancake. Rather, it means that parallel lines remain parallel across cosmic distances, and the angles of triangles add up to exactly 180 degrees, just as they do in the Euclidean geometry we learned in school. But here's where it gets beautifully complex. This flatness exists in a space that's simultaneously expanding, carrying galaxies away from each other like raisins in rising bread dough. The fabric of space itself is stretching, and yet the underlying geometry remains stubbornly flat, a cosmic coincidence that seems almost too precise to be accidental. This flatness has profound implications for the fate of everything. If the universe is truly flat, it will expand forever, gradually cooling and dimming as the stars burn out and black holes evaporate into Hawking radiation. It's a future that sounds melancholy, but operates on timescales so vast that entire civilizations could rise and fall billions of times over before the final cosmic winter sets in. Yet the story of cosmic shape isn't quite so simple as flat versus curved. There are subtleties and mysteries that keep cosmologists awake at night. The universe might be flat on the largest scales, but curved or twisted in ways we haven't yet detected. It might have a topology that's far stranger than anything we can easily visualize, perhaps folding back on itself in dimensions we can't directly perceive. Some theories suggest the universe might be like a cosmic donut, technically called a torus, where traveling far enough in one direction eventually brings you back to where you started, or it might have the topology of a Klein bottle, a mathematical object that has no true inside or outside. These possibilities sound like science fiction, but they're serious contenders in our quest to understand the cosmic architecture. The tools we use to probe these mysteries are marvels of human ingenuity, space based telescopes that can detect the faintest whispers of light from the edge of the observable universe, supercomputers that can simulate the evolution of cosmic structure across billions of years of time, and mathematical frameworks that allow us to translate observations into insights about the deepest nature of reality. One of the most intriguing aspects of cosmic geometry is how it connects to the very beginning of everything during the first fraction of a second after the Big Bang. The universe underwent a period of exponential expansion called cosmic inflation. This brief but dramatic stretching smoothed out any initial curvature, much like inflating a balloon makes its surface appear flatter to an ant walking on it. Inflation theory elegantly explains why the universe appears so flat today. Any initial curvature would have been stretched to nearly imperceptible levels, making the cosmos appear geometrically flat, even if it isn't perfectly so. It's like being placed on the surface of a sphere so large that the curvature becomes impossible to detect locally. Everything appears flat, even though you're actually walking on a curved surface. But inflation raises its own questions. What caused this extraordinary expansion, and why did it stop when it did? Some theories propose that inflation is an eternal process, creating an infinite multiverse of bubble universes, each with its own physical laws and geometric properties. In this scenario, our observable universe would be just one small region in a vast cosmic foam, each bubble potentially having its own unique shape and destiny. The mathematics of cosmic shape draws from some of the most beautiful areas of geometry and topology. Differential geometry helps us understand how space-time can be curved by matter and energy, while topology explores the global structure of space, the possible ways it can be connected and folded. These mathematical tools allow cosmologists to translate telescope observations into insights about the fundamental nature of reality itself. As we peer deeper into space and further back in time, we're essentially conducting archaeology on the universe itself. Each observation is like uncovering another fragment of cosmic history, helping us piece together the story of how the universe evolved from its hot, dense beginning to the vast, intricate structure we observe today. The shape of space is intimately connected to this evolutionary tale. The cosmic web, the largest scale structure in the universe, reveals itself as a magnificent tapestry of filaments and voids, galaxies strung along invisible threads of dark matter, creating patterns that span hundreds of millions of light years. This web like structure provides another window into cosmic geometry, showing us how matter and space have danced together across cosmic time. Dark matter and dark energy, those mysterious components that make up most of the universe, also play crucial roles in determining cosmic shape. Dark matter provides the gravitational scaffolding on which galaxies and larger structures form, while dark energy drives the accelerating expansion that will ultimately determine the universe's fate. The interplay between these invisible influences shapes the cosmic architecture in ways we're only beginning to understand. The relationship between cosmic shape and the forces that govern our universe runs deeper than we might initially imagine. When Einstein first proposed his theory of general relativity, he gave us a new way to think about gravity, not as a mysterious force pulling objects together, but as the curvature of space-time itself. Massive objects, like stars and planets, create dimples and warps in the fabric of space, much like a bowling ball placed on a stretched rubber sheet. This insight revolutionized our understanding of cosmic architecture because it revealed that matter and geometry are intimately connected. The distribution of mass and energy throughout the universe directly influences how space curves and bends, which in turn affects how matter moves and clusters together. It's a cosmic feedback loop where geometry shapes matter and matter shapes geometry in an endless dance of mutual influence. When we observe distant supernovas, those brilliant stellar explosions that can outshine entire galaxies, we're witnessing cosmic rulers that help us measure the expansion history of the universe. These standard candles, as astronomers call them, allow us to trace how the rate of expansion has changed over billions of years. revealing the subtle interplay between matter radiation and the mysterious dark energy that seems to be pushing space apart. The precision required to determine cosmic shape is almost incomprehensible. We're talking about measurements that must be accurate to within fractions of a percent across distances spanning billions of light years. It's like trying to determine whether the Earth is perfectly round by examining the curvature of your backyard with a ruler made of spider silk. Yet somehow, through ingenious techniques and collaborative efforts, spanning decades, scientists have managed to peer into the cosmic architecture with remarkable clarity. One of the most elegant approaches to understanding universal geometry comes from studying the cosmic microwave background, that ancient light we mentioned earlier when cosmologists analyze the tiny temperature variations in this radiation. They're looking for specific patterns that would reveal the underlying curvature of space. Flat curved or saddle shaped universes each leave distinctive fingerprints in this primordial glow. The patterns they've discovered tell a fascinating story. The universe appears to be balanced on a knife edge between different possible geometries. The density of matter and energy seems to be precisely at the critical value that produces flat spacetime. This cosmic coincidence has led some scientists to wonder whether there might be deeper principles at work, perhaps anthropic reasoning that suggests we observe a flat universe because only such a universe could give rise to the complex structures necessary for life. But the story becomes even more intriguing when we consider that our observable universe, the region from which light has had time to reach us since the Big Bang, might be just a tiny fraction of a much larger cosmic structure beyond our cosmic horizon. There could be regions where space curves differently, where the laws of physics take on subtly different forms, or where the very notion of geometry might break down entirely. The concept of cosmic topology adds another layer of mystery to our quest for understanding shape. Topology deals with properties that remain unchanged even when space is stretched, twisted, or deformed. It asks questions like whether the universe has boundaries, whether parallel lines that never meet in our local region might eventually intersect somewhere far beyond our view, or whether traveling in a straight line for long enough might somehow bring you back to your starting point. Some of the most mind bending possibilities in cosmic topology involve spaces that are finite yet have no boundaries. Imagine living on the surface of a sphere. You could travel in any direction forever without ever reaching an edge, yet the total surface area would be finite. Now extend this concept to three-dimensional space, and you begin to glimpse some of the exotic possibilities that serious cosmologists consider when modeling the universe's global structure. The mathematics describing these possibilities draws from abstract areas of geometry that would have seemed like pure intellectual curiosity just a century ago. Yet today, these mathematical frameworks provide the language we need to interpret observations from the most sophisticated instruments ever built by human civilization. It's a beautiful example of how abstract mathematical thinking can eventually illuminate the deepest mysteries of physical reality. Recent observations have pushed the boundaries of our cosmic understanding even further. Gravitational wave detectors that can sense ripples in spacetime smaller than a thousandth. The width of a proton have opened an entirely new window into the universe's architecture when massive black holes collide billions of light years away. They send gravitational waves racing through the cosmos, carrying information about the nature of space and time itself. These gravitational messengers provide an independent way to probe cosmic geometry because they travel through space-time differently than light waves do by comparing gravitational wave observations with traditional electromagnetic observations. Astronomers can test whether space truly behaves the way general relativity predicts and search for subtle deviations that might reveal new physics or unexpected aspects of cosmic structure. The interplay between quantum mechanics and cosmic geometry represents one of the most profound, unsolved puzzles in modern physics. Quantum field theory suggests that empty space isn't truly empty but filled with quantum fluctuations, virtual particles popping in and out of existence at the smallest scales. These quantum effects might influence the large scale structure of the universe in ways we're only beginning to understand. Some theories propose that the quantum nature of spacetime becomes important near the Big Bang itself, where the classical concepts of smooth geometry might break down entirely in this realm. Space and time might be granular, made up of discrete units, rather than the continuous fabric we observe on larger scales if true. This quantum geometry could hold clues to understanding not just the shape of our universe, but the fundamental nature of reality itself. The search for cosmic shape also connects to some of the deepest questions in theoretical physics. The hierarchy problem asks why gravity is so much weaker than the other fundamental forces. One possible answer involves extra dimensions beyond the three spatial dimensions we experience directly. These hidden dimensions might be curled up so small that we can't detect them directly, yet they could influence the overall geometry of our cosmic space. String theory, one of the leading candidates for a theory of quantum gravity, suggests that the fundamental constituents of reality are tiny vibrating strings existing in a space with many more dimensions than we observe. The way these extra dimensions are shaped and connected could determine the physical laws we observe in our three-dimensional worlds, making cosmic geometry not just a description of space, but a key to understanding why the universe works the way it does. As our observational capabilities continue to advance, we're entering an era of precision cosmology, where measurements of cosmic structure can test theoretical predictions with unprecedented accuracy. Upcoming surveys will map the positions and properties of billions of galaxies, allowing us to trace the cosmic web in exquisite detail and search for subtle signatures of exotic geometries or topologies. The James Webb Space Telescope, now peering deeper into space and further back in time than ever before, is revealing the universe as it existed when it was just a few 100 million years old. These observations of the cosmic dawn provide crucial tests of our understanding of how structure formed and evolved in the early universe, offering new constraints on the possible shapes and topologies of spacetime. Perhaps most remarkably, the quest to understand cosmic shape has practical implications for our understanding of fundamental physics. The techniques developed to analyze the cosmic microwave background have applications in medical imaging and data analysis. The computational methods used to simulate cosmic structure evolution have found uses in fields ranging from weather prediction to artificial intelligence. The story of cosmic shape reminds us that we live in an age of extraordinary discovery, where human curiosity and ingenuity have allowed us to probe the deepest mysteries of existence, from our small planet orbiting an ordinary star in an unremarkable galaxy. We've somehow managed to discern the architecture of the entire observable universe and glimpse possibilities that extend far beyond what we can directly observe. As we continue our gentle drift through these cosmic considerations, it's worth pausing to marvel at the sheer audacity of the scientific enterprise. The idea that creatures who evolved to navigate African savannas could eventually develop the mathematical tools and observational techniques needed to map the geometry of space-time itself speaks to something profound about the nature of intelligence and its relationship to the cosmos. The universe, it seems, has given rise to beings capable of contemplating its own structure, asking questions about its shape, its history, and its ultimate destiny. Whether this represents some deeper purpose or is simply an extraordinary accident in the cosmic lottery remains one of the most profound mysteries we face. But the very fact that we can ask such questions suggests something beautiful about our place in the grand scheme of things. The implications of cosmic shape extend far beyond abstract mathematics into the very heart of what it means to exist in this universe. Every atom in your body, every thought in your mind, every breath you take is shaped by the geometric framework that governs reality itself. When you look up at the night sky, you're not just seeing distant lights, you're witnessing the consequences of cosmic architecture playing out across billions of years. Consider for a moment the profound interconnectedness. This reveals the calcium in your bones was forged in the nuclear furnaces of dying stars. The iron in your blood was scattered across space by ancient supernova, and the very atoms that make up your thoughts were once part of primordial clouds drifting through the cosmic web. This isn't poetic metaphor, it's literal truth. We are made of star stuff, as Carl Sagan so beautifully put it, and that star stuff has been shaped by the geometry of space-time itself. The cosmic microwave background, that ancient echo of creation, carries within its patterns the seeds of everything we see today. Those tiny temperature fluctuations, just a few millionths of a degree apart, represent the quantum jitters of the early universe amplified by cosmic inflation into the vast structures we observe today. Galaxies, clusters, the cosmic web itself, all trace their ancestry back to those primordial whispers encoded in the geometry of space. This connection between the very small and the very large reveals one of the most elegant aspects of cosmic architecture: quantum fluctuations that existed when the universe was smaller than a proton have grown to become features spanning hundreds of millions of light years. It's as if the universe took a microscopic sketch and expanded it to cosmic proportions, preserving every delicate detail in the process. The search for cosmic shape has also led us to confront some of the most mind-bending concepts in modern physics. The notion of cosmic horizons suggests that there are regions of space from which light has not yet had time to reach us since the Big Bang beyond our observable universe. There might exist realms with entirely different properties, where the familiar laws of physics give way to stranger possibilities we can't yet imagine. Some cosmological models propose that our universe is just one bubble in an eternal cosmic foam, where new universes are constantly being born through quantum fluctuations or colliding brains higher dimensional membranes that exist in spaces we can't directly perceive. In such scenarios, the shape of our particular cosmic bubble might be just one possibility among an infinite array of geometric forms, each hosting its own unique version of reality. The anthropic principle raises the intriguing possibility that we observe a flat universe precisely because only such a universe could give rise to the complex chemistry necessary for life. If space were curved too severely, or if the expansion rate were significantly different, the delicate balance required for star formation, galaxy evolution, and ultimately biological complexity might never have emerged. We might exist in a universe fine tuned not by design, but by selection. Yet, even as we probe these cosmic mysteries, we must remember the limitations of our perspective. We are bound by the speed of light, constrained by the finite age of the universe, and limited by the resolution of our instruments. There may be aspects of cosmic geometry that remain forever beyond our reach, truths about the universe's shape that can never be directly observed from our particular vantage point in spacetime. The mathematical frameworks we use to describe cosmic shape represent some of humanity's greatest intellectual achievements. Differential geometry, tensor calculus, and topology provide the language needed to translate observations into understanding. These tools allow us to work with concepts that have no analog in everyday experience to manipulate equations, describing the curvature of 10-dimensional spaces or the topology of universe that loops back on itself. But perhaps the most remarkable aspect of our quest to understand cosmic shape is how it has transformed our sense of place in the universe. We've discovered that we live not in a static, unchanging cosmos, but in a dynamic, evolving structure that has been growing and changing for nearly 14 billion years. The universe has a history, a biography written in the distribution of galaxies, the abundance of elements, and the polarization patterns of ancient light. This historical perspective reveals that cosmic shape is not fixed, but evolutionary. The universe we observe today, with its large scale structure of filaments and voids, bears little resemblance to the smooth, nearly uniform cosmos that existed just a few 100,000 years after the Big Bang. The interplay between gravity, dark matter, and dark energy has sculpted space into the magnificent architecture we observe today. The role of dark energy in shaping cosmic geometry cannot be overstated. This mysterious component, which makes up roughly 70% of the universe's total energy content, is driving an accelerating expansion that will ultimately determine the fate of everything. If dark energy continues to dominate, the universe will expand exponentially, stretching space so rapidly that even nearby galaxies will eventually disappear beyond our cosmic horizon. This acceleration means that future astronomers billions of years from now might find themselves in a very different universe, one where the cosmic microwave background has been stretched to undetectable wavelengths, where distant galaxies have been carried beyond the reach of the most powerful telescopes, and where the evidence for the Big Bang and cosmic evolution has been erased by the relentless expansion of space. The measurement techniques used to determine cosmic shape represent marvels of precision and ingenuity. Astronomers can measure the positions of galaxies to accuracies better than 1 part in a million. They can detect gravitational lensing effects where massive clusters bend light from background galaxies, revealing the distribution of invisible dark matter. They can analyze the polarization of cosmic microwave background photons to infer conditions in the universe when it was just 380,000 years old. These observations require international collaborations involving thousands of scientists working with instruments scattered across the globe and orbiting in space. The data processing alone involves computational challenges that push the boundaries of what's possible, requiring supercomputers and algorithms that can handle data sets containing information about billions of cosmic objects. The philosophical implications of cosmic shape touch on some of humanity's deepest questions about existence and meaning. If the universe is truly infinite and flat, then somewhere beyond our cosmic horizon there might exist perfect copies of Earth, complete with identical versions of ourselves, living identical lives. The mathematics of infinite space suggests that every possible arrangement of matter must occur infinitely many times. Alternatively, if the universe has exotic topology, it might be finite yet unbounded, like the surface of a sphere but extended to 3 dimensions. In such a universe, you could theoretically travel in a straight line and eventually return to your starting point, having circumnavigated the entire cosmos, though such a journey would take far longer than the current age of the universe. The tools we've developed to study cosmic shape have applications far beyond cosmology. The statistical techniques used to analyze the cosmic microwave background have found uses in medical imaging, financial modeling, and climate science. The computational methods developed to simulate cosmic structure formation have applications in materials, science, biology, and artificial intelligence. As we push toward ever greater precision in mapping the universe's geometry, we're entering an era where cosmology becomes an experimental science capable of testing theoretical predictions with remarkable accuracy. The next generation of surveys will map the 3 dimensional positions of hundreds of millions of galaxies, allowing us to trace the cosmic web in unprecedented detail. These future observations may finally answer some of the deepest questions about cosmic architecture. Is the universe truly flat? Or might there be subtle curvature that we haven't yet detected? Does space have exotic topology that connects distant regions in unexpected ways? Are there signatures of extra dimensions or quantum gravity effects that we can observe in the large scale structure? The quest to understand the shape of the universe represents one of humanity's most ambitious intellectual endeavors. We're attempting to map the architecture of everything that exists, using tools and concepts that would have been unimaginable to previous generations. The fact that we can even contemplate such questions speaks to something profound about the nature of consciousness and its relationship to the cosmic order. As we continue our gentle exploration of these cosmic mysteries, it's worth remembering that we're not just passive observers of the universe, we're active participants in its evolution. Every measurement we make, every theory we develop, every insight we gain becomes part of the cosmic story itself. Intelligence and consciousness have emerged from the interplay of matter and geometry, creating beings capable of contemplating their own cosmic context. The universe through us has become self aware, capable of studying its own structure and pondering its own fate. This remarkable development suggests that consciousness might not be an accidental byproduct of cosmic evolution, but something more fundamental a natural consequence of the universe's drive toward greater complexity and organization. In our next gentle drift through these cosmic waters, we'll explore how the shape of space connects to the deepest questions about time causality and the nature of existence itself. For now, though, let yourself marvel at the extraordinary fact that from our small blue world, we've somehow managed to discern the architecture of everything, the relationship between cosmic geometry and the flow of time reveals perhaps the most elegant mystery in all of physics. When Einstein showed us that space and time are woven together into a single fabric, he opened a door to understanding how the shape of the universe influences not just where things are, but when they happen. The curvature of space-time doesn't just guide the motion of planets and galaxies, it orchestrates the very rhythm of existence itself. Imagine standing at different points in a gravitational field. Time itself flows at different rates near massive objects like black holes or neutron stars. Time slows to a crawl while in the vast empty regions between galaxies. It rushes forward at its maximum pace. This isn't science fiction. It's the lived reality of our curved cosmos, where the geometry of space determines the tempo of temporal passage. This temporal choreography has profound implications for our understanding of cosmic shape, because it means that the universe doesn't just exist in time, it creates time through its geometric structure. Every massive object, every cluster of dark matter, every ripple in the cosmic web contributes to a vast symphony of temporal variation that plays out across the cosmos. The cosmic microwave background, that ancient afterglow we've been exploring, carries within its patterns not just information about spatial geometry, but temporal signatures as well. Those tiny temperature fluctuations represent regions where time itself was flowing at slightly different rates in the early universe, creating patterns that we can still observe today, embedded in the fabric of space. When we peer into the depths of space with our most powerful telescopes, we're conducting a kind of temporal archaeology, looking back through layers of cosmic history. Each galaxy we observe exists at a different moment in the universe's past, creating a four-dimensional map that reveals how both space and time have evolved together since the beginning. The accelerating expansion, driven by dark energy, adds another layer to this temporal tapestry as space stretches faster and faster. It's not just carrying galaxies away from each other, it's fundamentally altering the relationship between space and time, creating a future where the cosmic horizon shrinks and distant regions of the universe become causally disconnected forever. This disconnection raises profound questions about the nature of reality itself. If two regions of space can no longer influence each other because the expansion of space prevents even light from traveling between them, do they still exist in the same universe? The geometry of space-time suggests that causality itself has boundaries beyond which events become cosmically irrelevant. The mathematics describing these phenomena draws from some of the most beautiful areas of theoretical physics. General relativity provides the framework for understanding how matter curves space-time, while quantum field theory in curved backgrounds explores how the quantum vacuum responds to geometric distortion. Together, these theories paint a picture of reality where space, time, and matter dance together in intricate patterns. One of the most intriguing aspects of cosmic geometry is how it connects to the deepest puzzles about the nature of information itself. When matter falls into a black hole, it seems to disappear from our universe, yet the information it carried cannot simply vanish according to the fundamental principles of quantum mechanics. This information paradox suggests that our understanding of space-time and causality may be incomplete. Some theories propose that information is preserved on the boundaries of spatial regions, much like a hologram stores three-dimensional information on a two-dimensional surface. This holographic principle suggests that the geometry of space might be more fundamental than we realize, with the interior structure of regions being determined by information encoded on their boundaries. The cosmic web, the magnificent tapestry of filaments and voids that spans the observable universe, represents the largest scale manifestation of geometric principles at work. Dark matter, the invisible scaffolding that makes up most of the universe's mass, follows geodesics through curved spacetime, creating structures that reveal the underlying geometry through their patterns and connections. These dark matter filaments act like cosmic highways along which ordinary matter flows, eventually forming the galaxies and stars we observe. The shape of these structures carries information about the curvature of space, the nature of dark energy, and the quantum fluctuations that seeded all cosmic structure in the first place. Recent discoveries in gravitational wave astronomy have opened entirely new windows into cosmic geometry. When massive black holes spiral into each other, they create ripples in space-time that carry information about the most extreme gravitational environments in the universe. These waves provide independent measurements of cosmic distances and expansion rates, offering new ways to probe the overall shape of space. The detectors that sense these gravitational whispers represent marvels of precision engineering, capable of measuring changes in distance smaller than 1/10,000th the width of a proton. Yet these incredibly sensitive instruments can trace the merger of black holes billions of light years away, revealing how space-time itself responds to the most violent events in the cosmos. The connection between cosmic shape and the fundamental constants of physics runs deeper than we might initially imagine. The strength of gravity, the speed of light, the mass of elementary particles, all these seemingly fixed properties of reality might actually depend on the geometric structure of the universe itself. Some theories suggest that what we perceive as constants might vary across different regions of space. This possibility opens up extraordinary questions about the nature of physical law itself. If the geometry of spacetime can influence the fundamental parameters that govern reality, then different regions of the universe might operate according to subtly different physics. The shape of space becomes not just a description of cosmic architecture, but a determinant of the very rules by which matter and energy behave. The anthropic principle takes on new significance. In this context, perhaps we observe the particular geometric properties we do not because they're inevitable, but because only universes with these specific characteristics can give rise to the complex chemistry necessary for life. The flatness of space, the strength of dark energy, the rate of cosmic expansion, all might be selected from a vast ensemble of possibilities. The search for extra dimensions represents one of the most ambitious frontiers in our quest to understand cosmic geometry. Theories like string theory and extra dimensional models propose that our familiar three dimensional space is embedded in a higher dimensional reality where additional spatial dimensions might be curled up, compactified, or otherwise hidden from direct observation. These hidden dimensions, if they exist, could profoundly influence the geometry we observe in our three-dimensional slice of reality. They might explain why gravity is so much weaker than other fundamental forces, provide natural candidates for dark matter and dark energy, or offer pathways to unifying all the forces of nature into a single geometric framework. The mathematical tools needed to explore these possibilities push the boundaries of human imagination. We work with concepts like Calabi-Yau, manifolds complex geometric objects that exist in six-dimensional spaces, or consider topological defects like cosmic strings and domain walls that might thread through the fabric of space-time, creating exotic geometric structures. Recent advances in computational cosmology have allowed scientists to simulate the evolution of cosmic structure with unprecedented detail. These virtual universes, running on the world's most powerful supercomputers, can model the gravitational dance of trillions of dark matter particles across billions of years, revealing how geometry and matter interact to create the cosmic web we observe. These simulations serve as laboratories for testing our understanding of cosmic shape by comparing the structures that emerge in virtual universes with the patterns we observe in the real cosmos. Scientists can constrain theories about dark matter, dark energy, and the fundamental nature of space-time itself. The role of quantum mechanics in shaping cosmic geometry remains one of the deepest unsolved problems in physics. Quantum field theory suggests that empty space is filled with virtual particles constantly appearing and disappearing in quantum fluctuations. These vacuum fluctuations should contribute to the curvature of space-time, yet their predicted effects are vastly larger than what we observe. This cosmological constant problem represents one of the most significant discrepancies between theory and observation in all of physics. The quantum vacuum should curve space so severely that the universe would collapse or expand catastrophically, yet somehow the actual curvature is incredibly small, allowing for the gentle expansion. We observe some solutions to this puzzle invoke the multiverse concept, suggesting that we exist in a universe where quantum fluctuations happen to largely cancel out, leaving behind just the tiny residual curvature needed for cosmic structure formation. In this view, our flat universe is not typical, but represents a rare fluctuation in an infinite ensemble of possible geometric configurations. The measurement of cosmic shape has evolved from philosophical speculation to precision science in just over a century. The techniques we use today can determine the curvature of space to accuracies of better than 1%, constraining theoretical models and ruling out entire classes of cosmic geometries that seemed plausible just decades ago. This precision has been achieved through the collaborative efforts of thousands of scientists working with instruments that represent the pinnacle of human technological achievement, space-based telescopes that can detect individual photons from the edge of the observable universe, particle accelerators that recreate conditions from the first moments after the Big Bang, and computational simulations that model the evolutions of cosmic structure across billions of years. The data flowing from these observations is reshaping our understanding of reality itself. We've discovered that the universe is dominated by mysterious dark components that we don't fully understand. We've found that space is expanding at an accelerating rate, driven by an unknown form of energy, and we've realized that the geometry we observe might be just a shadow of a higher dimensional reality. As we stand on the threshold of even more powerful observational capabilities, the next generation of cosmic surveys promises to push our understanding of geometric architecture to new frontiers. Projects like the Euclid Space Telescope, the Vera Rubin Observatory, and the Square Kilometer Array will map the universe in unprecedented detail, potentially revealing new aspects of cosmic shape that we haven't yet imagined. These future observations might finally answer some of the deepest questions about the nature of space and time. Is the universe truly infinite, or does it have finite size with exotic topology? Are there signatures of quantum gravity, effects that we can observe in the cosmic microwave background? Do extra dimensions leave detectable imprints on the large scale structure we see today? The philosophical implications of cosmic geometry continue to challenge our understanding of existence and meaning. If the universe is truly infinite, then every possible arrangement of matter, including perfect copies of ourselves, must exist somewhere beyond our cosmic horizon. This suggests a reality far stranger and more expansive than anything our ancestors could have imagined. Alternatively, if space has finite volume with complex topology, then the universe might be smaller than we think. But connected in unexpected ways, you might be able to look in one direction and see the back of your own head, though the light would have traveled for billions of years to complete its cosmic circuit. The relationship between consciousness and cosmic geometry raises profound questions about the nature of observation and reality. Quantum mechanics suggests that measurement plays a fundamental role in determining physical properties. But what does this mean for the geometry of space-time itself? Are we passive observers of cosmic shape or active participants in its determination? Some interpretations of quantum mechanics propose that consciousness itself might play a role in shaping reality through the act of observation. If true, then the emergence of intelligent observers in the universe might not be a mere accident, but a necessary component in the cosmic architecture, a universe that becomes self aware through the evolution of conscious beings. The practical applications of our quest to understand cosmic shape extend far beyond pure science. The mathematical techniques developed for analyzing cosmic structure have found uses in medical imaging, financial modeling, and artificial intelligence. The computational methods used to simulate gravitational interactions have applications in engineering and materials science. The technological spin offs from cosmic research have repeatedly transformed human civilization. Global positioning systems rely on precise understanding of relativistic effects. Radio astronomy led to the development of wireless communication, and the World Wide Web was originally created to help particle physicists share data about fundamental physics. As we continue our gentle exploration of these cosmic mysteries, we're reminded that the quest to understand the shape of the universe is ultimately a quest to understand ourselves. We are made of atoms forged in stellar cores, organized by the same geometric principles that govern cosmic structure. Our thoughts and dreams emerge from patterns of electrical activity that follow the same mathematical laws that describe the curvature of space-time. The universe through us has become capable of contemplating its own architecture, asking questions about its geometry, its history, and its ultimate fate. This remarkable development suggests that intelligence and consciousness might not be accidental byproducts of cosmic evolution, but natural consequences of the universe's drive toward greater complexity and self understanding in the gentle darkness of space between the galaxies. Quantum fluctuations continue to whisper their secrets, creating virtual particles that borrow energy from the vacuum only to disappear again in fractions of a second. These quantum whispers might hold clues to the deepest nature of reality, revealing connections between the microscopic world of particles and the cosmic scale geometry of space-time. The story of cosmic shape is still being written with each new observation, each theoretical breakthrough, each computational simulation, adding new chapters to our understanding. We stand at a unique moment in cosmic history when the universe has evolved conscious observers capable of mapping its own structure and pondering its own mysteries. As we drift toward our next gentle exploration of these cosmic waters, we'll delve into how the shape of space connects to the deepest questions about the nature of reality itself. The relationship between geometry and information, the possibility of multiple universes, and the ultimate fate of everything that exists for now. Let yourself rest in the wonder of knowing that every breath you take, every thought you think, occurs within the magnificent geometric framework that encompasses all of existence. The quest to understand cosmic shape has led us to one of the most beautiful paradoxes in all of science. The more precisely we measure the universe, the more mysterious it becomes. Each answer we uncover seems to reveal three new questions, like opening a cosmic matryoshka doll, where each layer contains not just smaller versions of itself, but entirely different puzzles altogether. It's as if the universe enjoys keeping us guessing, offering us glimpses of its secrets, while always maintaining an air of elegant mystery. Consider the peculiar relationship between cosmic flatness and the horizon problem. When we observe the cosmic microwave background, we see that regions of space that should never have been in contact with each other since the Big Bang display remarkably similar temperatures. It's like finding that two people who have never met, never communicated, and lived on opposite sides of the world somehow decided to wear exactly the same outfit on the same day. This cosmic coincidence suggests that our understanding of space, time, and causality might be missing some crucial pieces. The solution, cosmic inflation, proposes that space itself underwent a period of exponential expansion in the first fraction of a second after the Big Bang. During this brief but dramatic stretching, regions that were once in close contact were carried far apart, preserving their similar properties across vast distances. It's a beautiful theory that elegantly explains the observed flatness and uniformity of space, yet it raises profound questions about what lies beyond our observable cosmic bubble. If inflation is correct, then our entire observable universe, with its hundreds of billions of galaxies, might be just one tiny region in an incomprehensibly vast cosmic ocean. Beyond our cosmic horizon, there could exist realms where the laws of physics take on different forms, where space curves in ways we've never imagined, or where the very concepts of matter and energy might not apply. We're like islanders discovering that their entire world is just one small atoll in an infinite archipelago. The mathematics describing these possibilities ventures into territory that challenges our deepest intuitions about reality. We work with concepts like eternal inflation, where new universes are constantly being born through quantum fluctuations, each potentially having its own unique geometric properties. Some of these cosmic bubbles might expand forever, others might collapse back on themselves, and still others might evolve according to physical laws so different from our own that they defy description. The anthropic landscape that emerges from these considerations is both humbling and extraordinary. If there truly are infinite variations of cosmic geometry scattered across an eternal multiverse, then the particular shape we observe, the specific balance of forces that allows for stars, planets, and life itself, might represent just one possibility among countless others. We exist in a universe with flat geometry, not because it's inevitable, but because observers like us can only emerge in cosmic environments that permit the complex chemistry of life. This perspective transforms our understanding of cosmic fine tuning, the remarkable precision with which the fundamental constants seem adjusted to allow for complexity and consciousness no longer requires explanation through design or cosmic coincidence. Instead, it emerges naturally from a selection effect, a kind of observational bias where conscious beings can only find themselves in universes capable of producing consciousness. Yet, even as these theoretical frameworks expand our conception of reality, they raise troubling questions about the nature of scientific knowledge itself. If our universe is just one bubble in an infinite foam, how can we ever hope to test theories about the larger cosmic structure? The very success of the anthropic principle in explaining cosmic fine tuning might paradoxically limit our ability to predict or understand the broader multiverse of which we're supposedly part. The tools we use to probe these mysteries continue to evolve at a breathtaking pace. Machine learning algorithms now sift through vast datasets from cosmic surveys, identifying patterns and correlations that human researchers might never have noticed. Artificial intelligence helps us design new observational strategies, optimize telescope pointings, and even discover new ways to extract information from the subtle distortions in the cosmic microwave background. These computational approaches have revealed unexpected connections between cosmic geometry and information theory. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram stores three-dimensional images on a two-dimensional surface. This radical idea implies that our three-dimensional experience of reality might be a kind of projection from information stored on a distant cosmic boundary. If the holographic principle is correct, then the shape of space itself might be less fundamental than we imagine. What we perceive as geometric properties, curvature, distance, and dimensionality could all emerge from more basic informational relationships. It's a perspective that turns our usual understanding inside out, suggesting that information rather than geometry might be the truly fundamental substrate of reality. The connection between cosmic shape and quantum entanglement adds another layer of mystery to this already complex picture. Recent research suggests that the fabric of space-time itself might be woven from quantum entanglement, with the geometric properties we observe emerging from the correlations between quantum systems. When particles become entangled, they create connections that transcend ordinary spatial separation, suggesting that space itself might be a secondary phenomenon arising from more fundamental quantum relationships. This quantum geometry operates according to principles that seem to defy our everyday intuitions about space and distance. Entangled particles can influence each other instantaneously across arbitrary distances, creating connections that exist outside the normal geometric structure of spacetime. Some theorists propose that these quantum connections might be the threads from which the cosmic web is ultimately woven, with ordinary matter and energy representing excitations in this underlying quantum substrate. The search for experimental signatures of quantum geometry has led to some of the most ambitious scientific projects ever undertaken. Underground laboratories shield sensitive detectors from cosmic rays while searching for evidence of extra dimensions or quantum modifications to gravity. Space based interferometers measure gravitational waves with unprecedented precision, looking for subtle deviations from general relativity that might reveal the quantum nature of space-time itself. These experiments operate at the very limits of what's technically possible, requiring international collaborations and technologies that push the boundaries of human engineering. The fact that we can even contemplate such measurements speaks to the remarkable progress of scientific civilization, our collective ability to transform abstract mathematical concepts into concrete observational programs. The philosophical implications of quantum geometry extend far beyond physics into questions about the nature of existence itself. If space and time emerge from quantum entanglement, then the separation between different regions of the universe might be less absolute than we imagine. What we perceive as distant galaxies might be more intimately connected to us than the coffee cup on our table, linked through quantum correlations that transcend ordinary geometric relationships. This perspective suggests a kind of cosmic holism where every part of the universe contains information about every other part, where the boundary between self and cosmos becomes fluid and permeable. It's a vision that resonates with ancient mystical traditions while emerging from the most rigorous mathematical frameworks of modern physics, suggesting deep connections between scientific and spiritual ways of understanding reality. The role of consciousness in cosmic geometry remains one of the most tantalizing mysteries in all of science. Some interpretations of quantum mechanics suggest that observation plays a fundamental role in determining physical properties, raising questions about whether conscious observers might influence the shape of spacetime itself. If consciousness is necessary to collapse quantum superpositions, then the emergence of intelligent life in the universe might not be a mere accident, but a crucial component in the cosmic architecture. This participatory universe hypothesis proposes that reality is co created through the interaction between conscious observers and quantum systems. In this view, the universe doesn't simply exist independently of observation, but comes into being through the act of measurement and awareness. Consciousness becomes not just a byproduct of cosmic evolution, but an active participant in shaping the reality it observes. The implications of this perspective are both thrilling and unsettling. It suggests that we're not passive witnesses to cosmic history, but active participants in its unfolding, that our observations and measurements contribute to the ongoing creation of reality itself. The shape of the universe might not be fixed, and predetermined but constantly emerging through the collective observations of conscious beings throughout the cosmos. Recent developments in quantum cosmology have begun to explore these possibilities through rigorous mathematical frameworks. Researchers work with concepts like quantum superpositions of different cosmic geometries, where the universe exists in multiple states simultaneously until observation collapses it into a single reality. These ideas push the boundaries of both physics and philosophy, challenging our most basic assumptions about the nature of existence. The experimental verification of these quantum cosmological theories presents extraordinary challenges. How do you test whether the universe exists in superposition when any measurement you make necessarily collapses that superposition? It's like trying to observe Schrodinger's cat without opening the box, a fundamental limitation that might forever prevent us from directly confirming some of our deepest theoretical insights about cosmic geometry. Yet, even if we can never directly observe quantum superpositions of cosmic geometry, the mathematical frameworks describing these phenomena continue to yield surprising insights about the nature of space and time. They suggest connections between seemingly unrelated areas of physics, reveal hidden symmetries in the laws of nature, and point toward unified theories that might eventually encompass all the fundamental forces and particles in a single geometric framework. The search for this unified geometry represents perhaps the most ambitious goal in all of theoretical physics. If successful, it would reveal that electromagnetism, the weak nuclear force, the strong nuclear force, and gravity are all different aspects of a single geometric principle operating in higher dimensional space. The shape of the universe would then become not just a description of cosmic architecture, but the key to understanding why reality works the way it does. String theory, loop quantum gravity, and other approaches to quantum geometry each offer different visions of this unified framework. Some propose that fundamental particles are tiny vibrating strings in 10-dimensional space. Others suggest that space itself is made of discrete quantum units, and still others explore the possibility that geometry emerges from purely informational principles. Each approach paints a different picture of cosmic shape, yet all share the beautiful vision of a universe where mathematics and reality merge into a single, elegant whole. The technological implications of understanding cosmic geometry extend far beyond pure science into possibilities that seem almost magical from our current perspective. If we could manipulate the fabric of space time itself, we might be able to create shortcuts through higher dimensions, generate unlimited energy from quantum vacuum fluctuations, or even engineer pocket universes with customized physical laws. These possibilities remain highly speculative, requiring advances in our understanding of physics that might take centuries or millennia to achieve. Yet the history of science suggests that today's impossible dreams often become tomorrow's everyday technologies. The quantum mechanics that now powers our computers and smartphones once seemed like pure mathematical abstraction with no practical applications. As we drift deeper into these cosmic contemplations, it's worth pausing to appreciate the extraordinary journey that has brought us to this point. In just a few centuries, human civilization has progressed from viewing the Earth as the center of creation to mapping the geometry of space-time itself. We've discovered that we live in an expanding universe filled with dark matter and dark energy, potentially just one bubble in an infinite multiverse where consciousness itself might play a fundamental role in shaping reality. This transformation, in our cosmic perspective, represents one of the greatest intellectual achievements in human history, comparable to the development of language, agriculture, or the scientific method itself. We've learned to see ourselves not as separate from the universe, but as expressions of it, conscious manifestations of the same geometric principles that govern the motion of galaxies and the quantum dance of elementary particles. The story of cosmic shape is ultimately a story about the power of human curiosity and imagination. From our small planet orbiting an ordinary star, we've somehow managed to glimpse the architecture of everything, to ask questions about the nature of existence itself, and to develop mathematical frameworks capable of describing realities far beyond our direct experience. This achievement suggests something profound about the relationship between mind and cosmos, between consciousness and geometry. Perhaps the universe's capacity to understand itself through conscious observers like us is not an accident, but a fundamental feature of reality, a cosmic principle as basic as the conservation of energy or the speed of light. As we prepare to venture even deeper into these mysteries, to explore the connections between cosmic shape and the ultimate questions about existence, meaning, and destiny, let yourself marvel at the simple fact that such questions can even be asked. In a universe governed by geometric principles, consciousness has emerged as a way for space and time to contemplate their own nature, for the cosmos to know itself through the minds it has created. The gentle darkness between the stars whispers of geometries we have yet to discover, of connections we have yet to understand, and of possibilities we have yet to imagine. In that darkness, quantum fields fluctuate according to mathematical laws, creating virtual particles that briefly borrow energy from the vacuum before returning to the void. These quantum whispers might hold the keys to understanding not just the shape of our universe, but the nature of reality itself. The dance between observation and reality becomes even more intricate when we consider how the very act of measuring cosmic shape might influence what we discover. Every photon that reaches our telescopes carries information that has traveled for billions of years through the evolving geometry of spacetime itself. These ancient messengers have been stretched by cosmic expansion, deflected by gravitational lenses, and subtly altered by their journey through the quantum foam that might exist at the smallest scales of reality. When we analyze the cosmic microwave background, we're not just looking at a snapshot of the early universe, we're examining light that has been shaped by every twist and curve in spacetime it encountered along its cosmic voyage. The patterns we observe might tell us as much about the journey as they do about the destination, revealing how space itself has evolved and changed over the eons since those photons first began their trek toward Earth. This temporal archaeology of light creates a kind of cosmic detective story where each clue must be carefully interpreted in the context of the universe's changing geometry. The redshift of distant galaxies tells us about expansion rates, but it also carries information about the curvature of the paths that light has taken through space. The polarization patterns in the cosmic microwave background reveal not just primordial conditions, but also the gravitational waves that might have rippled through space-time during the universe's first moments. The precision required to extract these subtle signals pushes our instruments and analysis techniques to their absolute limits. We're looking for deviations of parts per million in temperature measurements, searching for correlations across angular scales that span the entire visible sky, and trying to separate genuine cosmic signals from the myriad sources of noise and contamination that can mask the whispers of spacetime itself. Perhaps most remarkably, the quest to understand cosmic shape has revealed deep connections between the largest and smallest scales in nature. The quantum fluctuations that existed when the universe was smaller than an atom have grown to become the cosmic web of filaments and voids that spans billions of light years. It's as if the universe took a quantum sketch and inflated it to cosmic proportions, preserving every microscopic detail in the process. This connection between quantum mechanics and cosmic geometry suggests that the shape of space might be fundamentally probabilistic rather than deterministic. Just as quantum particles exist in superpositions of multiple states until observed, the universe itself might exist in a superposition of different geometric configurations, with our observations somehow selecting which version of reality we experience. The mathematics describing these quantum geometries ventures into territory that challenges our most basic intuitions about space and time. We work with concepts like quantum foam, where space-time itself becomes uncertain and fluctuating at the smallest scales, dissolving into a probabilistic froth of virtual particles and ever-changing geometric relationships. At these scales, the smooth, continuous fabric of space that we experience in everyday life gives way to something far stranger and more dynamic. Some theories propose that space and time themselves might be emergent properties arising from more fundamental quantum information. In this view, and what we perceive as geometric relationships, distances, angles, and curvatures might all be collective behaviors emerging from vast networks of quantum entanglement. It's like discovering that what you thought was a solid surface is actually made of countless tiny dancers whose coordinated movements create the illusion of stability and structure. The holographic principle takes this idea even further, suggesting that all the information in a volume of space can be encoded on its boundary surface. This radical proposal implies that our three-dimensional experience might be a kind of projection from information stored in two dimensions, like a cosmic hologram, where depth is an illusion created by the interference patterns of more fundamental waves. If this principle is correct, then the question of cosmic shape becomes even more mysterious. Are we asking about the geometry of a three-dimensional space that might not be fundamentally real, or should we be trying to understand the two-dimensional surfaces from which our reality is somehow projected? It's a puzzle that turns our usual understanding of space inside out, suggesting that the universe might be far stranger than even our wildest theoretical speculations imagine. The search for experimental evidence of these exotic geometric principles has led to some of the most ambitious scientific collaborations in human history. Gravitational wave detectors that can sense ripples in spacetime smaller than a thousandth the width of a proton search for signatures of extra dimensions or quantum modifications to general relativity. Underground laboratories shield particle detectors from cosmic rays, while looking for evidence that space itself might be quantized at the smallest scales. These experiments represent marvels of human ingenuity and international cooperation. Scientists from dozens of countries work together to design instruments capable of measuring effects so subtle they barely register above the quantum noise that pervades all physical systems. The fact that we can even contemplate such measurements speaks to something profound about the relationship between consciousness and cosmos, our ability to transcend the limitations of our biological origins through mathematics and technology. The philosophical implications of quantum geometry extend far beyond physics into questions about the nature of existence itself. If space and time emerge from quantum entanglement, then the boundaries between different regions of the universe might be far more fluid than we imagine. What appears to be empty space between galaxies could be filled with invisible connections, quantum correlations that link distant parts of the cosmos in ways that transcend ordinary geometric relationships. This quantum holism suggests a universe where every part contains information about every other part, where the separation between observer and observed becomes a matter of perspective rather than absolute truth. It's a vision that resonates with contemplative traditions while emerging from the most rigorous mathematical frameworks of modern physics, hinting at deep connections between scientific and spiritual ways of understanding reality. The role of information in cosmic geometry has become one of the most active areas of theoretical research. Some physicists propose that information, rather than matter or energy, might be the fundamental substrate from which everything else emerges. In this view, particles are information processing systems, forces are information transfers, and spacetime itself is a kind of cosmic computer where reality is computed through the interactions of quantum bits. This computational perspective on cosmic geometry opens up extraordinary possibilities. If the universe is indeed a vast information processing system, then understanding its shape becomes a question of understanding its computational architecture. The cosmic web of dark matter filaments might represent the hardware on which cosmic computations run, while the flow of matter and energy through these structures could be the software that generates the reality we observe. The implications for consciousness are particularly intriguing. If the universe is computational in nature, then conscious observers might not just be passive witnesses to cosmic processes, but active participants in the universe's ongoing calculation of itself. Our thoughts, observations, and measurements could be part of the cosmic computation, contributing to the ongoing creation and evolution of space-time geometry. Recent developments in quantum information theory have begun to formalize these ideas through concepts like quantum error correction and emergent spacetime. Researchers have discovered that certain quantum systems naturally generate geometric structures that behave like curved spacetime, suggesting that gravity itself might emerge from quantum information processing rather than being a fundamental force of nature. These developments point toward a future where our understanding of cosmic shape will be intimately connected to our understanding of computation, information, and consciousness. The geometry of the universe might not be something we discover through observation alone, but something we participate in creating through our attempts to understand it. Reality becomes a collaborative process between conscious observers and the quantum systems they study. The practical implications of this quantum informational view of geometry could be profound. If space-time emerges from quantum computation, then mastering the principles of quantum information might eventually allow us to manipulate geometric properties directly. We might learn to create regions of altered space-time, generate gravitational fields through quantum control, or even engineer pocket universes with customized physical laws. Such possibilities remain highly speculative, requiring advances in our understanding that might take centuries to achieve. Yet the history of physics suggests that theoretical insights often lead to practical applications in ways that were completely unforeseeable when the theories were first developed. The quantum mechanics that seemed like pure mathematical abstraction a century ago now powers the computers and smartphones that have revolutionized human civilization. The measurement of cosmic shape continues to push the boundaries of observational astronomy into new frontiers. Future space telescopes will map the positions and properties of billions of galaxies with unprecedented precision, allowing us to trace the cosmic web in exquisite detail and search for subtle signatures of exotic geometries or quantum effects. These observations might finally reveal whether space has hidden dimensions, exotic topology, or quantum modifications that we haven't yet detected. The data volumes involved in these future surveys will be staggering, requiring new approaches to data analysis and storage that push the limits of computational technology. Machine learning algorithms will sift through datasets containing information about billions of cosmic objects, searching for patterns and correlations that human researchers could never identify manually. The universe itself will become a big data problem, requiring the full power of artificial intelligence to decode its geometric secrets. As these observational capabilities advance, we're entering an era where cosmology becomes an increasingly precise experimental science. Theoretical predictions about cosmic geometry can be tested with remarkable accuracy, ruling out entire classes of models and constraining the parameters that describe the universe's shape and evolution. This precision brings both opportunities and challenges, as our theories must become correspondingly more sophisticated to match the quality of the data. The international nature of modern cosmological research reflects the global scope of the questions we're trying to answer. Understanding the shape of the universe requires combining observations from telescopes scattered across the Earth and orbiting in space, theoretical insights from research groups on every continent, and computational resources that span multiple countries. It's a collaborative effort that transcends national boundaries and political divisions, united by our shared curiosity about the cosmos. This global scientific enterprise represents one of humanity's greatest collective achievements, comparable in scope and ambition to the construction of cathedrals or the exploration of new continents. We're engaged in a project that spans generations, building upon the work of previous researchers while laying foundations for discoveries that won't be fully realized for decades to come. The cultural impact of our evolving understanding of cosmic shape extends far beyond the scientific community into art, literature, philosophy, and everyday conversation. The realization that we live in a universe whose geometry might be quantum mechanical, holographic, or computational in nature has begun to influence how we think about reality, consciousness, and our place in the grand scheme of things. Artists and writers draw inspiration from cosmological discoveries, creating works that explore the aesthetic and emotional dimensions of curved spacetime, quantum geometry, and cosmic topology. Musicians compose pieces that attempt to capture the mathematical harmonies underlying cosmic structure, while filmmakers and novelists explore the philosophical implications of living in a universe where space and time might be emergent properties of something more fundamental. The educational challenges of communicating these ideas to broader audiences are considerable. How do you explain the concept of emergent spacetime to someone without advanced training in mathematics and physics? How do you convey the beauty and significance of discoveries about cosmic geometry in ways that inspire rather than intimidate? These challenges require new approaches to science communication that bridge the gap between technical precision and human understanding. Perhaps most importantly, our growing understanding of cosmic shape is transforming our sense of what it means to be human in this universe. We're learning that we're not separate from the cosmic geometry we study, but intimately connected to it, made of atoms that were forged in stellar cores and organized according to the same mathematical principles that govern the largest structures in space. This perspective suggests a kind of cosmic citizenship where our responsibilities extend beyond our planet or even our galaxy to encompass our role as conscious participants in the universe's ongoing evolution. If consciousness plays a fundamental role in shaping reality through observation and measurement, then every conscious being becomes a co creator of the cosmic architecture we inhabit. The future of cosmic geometry research promises discoveries that will continue to revolutionize our understanding of reality itself. As our observational capabilities become more sophisticated and our theoretical frameworks more comprehensive, we may finally answer some of the deepest questions about the nature of space, time, and existence. We might discover that the universe has hidden dimensions that we can learn to access, that space time is quantized in ways that allow for new forms of technology, or that consciousness itself is woven into the fundamental structure of geometric reality. Yet, even as we push toward these extraordinary possibilities, the basic wonder that drives our quest remains unchanged. We look up at the night sky and ask the same questions that have puzzled humans for millennia. What is this place we call home? How big is it? What shape does it have? Where did it come from? And where is it going? The fact that we can now approach these questions with mathematical precision and observational rigor doesn't diminish their fundamental mystery. It only makes them more beautiful and profound. In the gentle darkness between the stars, space itself continues its ancient dance, curving and flowing, according to laws we're only beginning to understand. Quantum fields fluctuate in the vacuum, creating virtual particles that briefly borrow energy from the void before returning to nothingness. Dark matter streams along invisible filaments, sculpting the cosmic web through gravitational interactions we can map but not yet fully explain. And somewhere in this vast geometric symphony, consciousness has emerged as the universe's way of contemplating its own structure, asking questions about its shape, and wondering at the elegance of its own mathematical foundations. As we continue our quiet journey Through these cosmic waters, we're reminded that the quest to understand the shape of the universe is ultimately a quest to understand ourselves. We are expressions of cosmic geometry, conscious manifestations of the same principles that govern the motion of galaxies and the quantum behavior of elementary particles. In seeking to understand the cosmos, we're exploring the deepest aspects of our own nature, discovering our place in the grand mathematical symphony that encompasses all of existence. The shape of the universe, whatever it may ultimately prove to be, contains within it the story of everything that has ever been or ever will be. It's a story written in the language of mathematics, performed on the stage of space-time, and witnessed by conscious observers who have somehow emerged from the very processes they seek to understand. And in that witnessing, in that quest for understanding, the universe achieves something remarkable. It becomes aware of itself, capable of contemplating its own infinite mystery and beauty. The story we've been gently unfolding together reveals something quite extraordinary about the nature of discovery itself. Each measurement we make, each theoretical insight we gain, doesn't just add another fact to our cosmic encyclopedia. Instead, it transforms the very ground on which we stand, shifting our perspective in ways that make yesterday's certainties seem quaint and tomorrow's possibilities seem almost magical. It's rather like learning to see color for the first time, only to discover that what you thought was the full spectrum was merely the faintest hint of something far more magnificent. Consider how the concept of cosmic shape has evolved in just the past few decades. When astronomers first began mapping the three-dimensional distribution of galaxies, they expected to find matter scattered more or less randomly throughout space, perhaps with a few clusters here and there, like islands in a cosmic sea. Instead, they discovered something that took their breath away: a vast web like structure spanning billions of light years, with galaxies strung along invisible filaments like dewdrops on spider silk, separated by enormous voids that seemed almost empty by comparison. This cosmic web, as it came to be known, revealed that the universe has an architecture far more intricate and beautiful than anyone had imagined. The filaments trace the underlying scaffolding of dark matter, that mysterious substance that makes up most of the universe's mass, yet interacts with ordinary matter only through gravity. These dark matter highways channel the flow of gas and stars, creating the luminous structures we observe, while remaining largely invisible themselves. It's as if we discovered that our familiar world of light and matter is merely the visible decoration on a vast invisible framework that shapes everything we see. The mathematical description of this cosmic architecture requires tools that would have seemed impossibly abstract to earlier generations of scientists. We work with concepts like correlation functions that measure how the clustering of matter varies across different scales, power spectra that reveal the statistical properties of cosmic structure, and topological measures that characterize the connectivity of the cosmic web itself. These mathematical tools allow us to translate the poetry of cosmic structure into the precise language of numbers and equations. Yet, even as we develop increasingly sophisticated ways to describe what we observe, the cosmos continues to surprise us with new layers of complexity and beauty. Recent observations have revealed that the cosmic web itself is not static but dynamically evolving. with filaments growing and connecting over billions of years while voids expand and empty out. It's like watching a vast three-dimensional tapestry being woven in slow motion, with each thread representing the gravitational dance of countless galaxies and dark matter halos. The role of dark energy in shaping this cosmic tapestry cannot be overstated. This mysterious component, which makes up roughly 70% of the universe's total energy density, acts like a kind of anti gravity that accelerates the expansion of space itself. As dark energy pushes space apart, it competes with gravity's tendency to pull matter together, creating a delicate balance that determines the final architecture of cosmic structure. Too little dark energy, and the universe would have collapsed back on itself long before galaxies could form. Too much, and space would expand so rapidly that matter could never clump together into the complex structures we observe. This cosmic tension between gravity and dark energy plays out differently at different scales, creating a hierarchy of structures that spans an enormous range of sizes. On the smallest scales, gravity dominates, allowing gas to collapse into stars and planets. On intermediate scales, the competition between the two forces shapes the formation of galaxies and galaxy clusters. On the largest scales, dark energy takes control, stretching space so rapidly that distant regions of the cosmic web become causally disconnected, unable to influence each other, even through the fastest possible signals traveling at the speed of light. The observational techniques we use to map this cosmic architecture represent marvels of human ingenuity and technological achievement. Modern surveys can measure the positions and distances of millions of galaxies with extraordinary precision, creating three-dimensional maps of cosmic structure that reveal patterns spanning billions of light years. These observations require careful calibration of complex instruments, sophisticated statistical analysis of vast data sets, and international collaborations involving hundreds of scientists working together across continents and time zones. One of the most elegant aspects of cosmic structure mapping involves the use of gravitational lensing, a phenomenon predicted by Einstein's general relativity, where massive objects bend the path of light passing near them. When light from distant galaxies travels through the cosmic web, it gets deflected by the gravitational fields of intervening dark matter structures, creating subtle distortions in the shapes of background galaxies that we can detect and analyze. It's like using the universe itself as a giant telescope, with dark matter acting as a lens that reveals its own distribution through the way it bends light. These weak lensing measurements provide one of our most powerful tools for mapping the invisible scaffolding of cosmic structure. By analyzing the tiny distortions in galaxy shapes across large areas of sky, astronomers can reconstruct the three-dimensional distribution of dark matter with remarkable precision. The resulting maps reveal the cosmic web in unprecedented detail, showing how dark matter filaments connect galaxy clusters and how vast voids separate different regions of the universe. The statistical properties of cosmic structure carry within them the signatures of the physical processes that shaped the universe's evolution. The way matter clusters on different scales reflects the interplay between gravity, dark energy, and the initial conditions set during the universe's first moments. By measuring these clustering patterns with high precision, cosmologists can constrain fundamental parameters like the amount of dark matter, the strength of dark energy, and even the properties of mysterious components, like dark radiation or primordial gravitational waves. This connection between cosmic structure and fundamental physics transforms astronomy into a kind of laboratory for testing our most basic theories about the nature of reality. The universe becomes an experiment that has been running for nearly 14 billion years, with the current distribution of galaxies serving as the final result that we can observe and analyze. It's an experiment of almost unimaginable scale and complexity, involving processes that operate across dozens of orders of magnitude in size and time. The computational challenges involved in modeling cosmic structure formation push the boundaries of what's possible with even the most powerful supercomputers. Simulating the gravitational interactions of billions of dark matter particles across billions of years requires algorithms that can handle the vast range of scales involved, from the smooth expansion of space on cosmic scales to the complex nonlinear dynamics of collapsing structures. These simulations serve as theoretical laboratories where we can test our understanding of cosmic evolution and make predictions that can be compared with observations. Modern cosmological simulations reveal cosmic structure formation as an extraordinarily beautiful and complex process. Starting from the nearly uniform conditions of the early universe, gravity gradually amplifies tiny density fluctuations, causing matter to flow along converging streams toward regions of higher density. Over billions of years, this cosmic choreography creates the intricate web like patterns we observe today, with dark matter halos growing and merging in a hierarchical process that builds up larger and larger structures over time. The emergence of complexity from simplicity in these simulations is truly remarkable to witness. What begins as nearly featureless initial conditions gradually develops into rich, intricate structures with filaments, nodes, and voids arranged in patterns that seem almost organic in their complexity. It's like watching a vast three-dimensional garden grow in fast forward, with cosmic flowers blooming at the intersections of dark matter streams and vast empty spaces opening up between the growing structures. The role of feedback processes in shaping cosmic structure adds another layer of complexity to this cosmic garden. Stars don't just form passively in response to gravitational collapse. They actively reshape their environments through stellar winds, supernova explosions, and the intense radiation they emit during their lifetimes. Supermassive black holes at the centers of galaxies can launch powerful jets that heat and disperse surrounding gas, preventing further star formation and affecting the growth of their host galaxies. These feedback mechanisms create a complex web of interactions between the smallest and largest scales in the universe. Understanding these feedback processes requires bringing together insights from many different areas of physics, from the nuclear reactions that power stars to the magnetohydrodynamics that governs the behavior of hot gas in galaxy clusters. It's a multidisciplinary endeavor that connects stellar physics, plasma physics, general relativity, and thermodynamics in a unified framework for understanding cosmic evolution. The universe becomes a vast laboratory where all the fundamental forces of nature work together to create the structures we observe. The philosophical implications of our growing understanding of cosmic architecture extend far beyond the technical details of structure formation and gravitational dynamics. We're learning that the universe is not just a collection of objects scattered through empty space, but a unified system where every component influences every other component through a complex web of physical relationships. The shape of space itself emerges from this web of interactions, with geometry and matter engaged in an eternal dance of mutual influence. This holistic view of cosmic structure challenges our tendency to think of the universe in terms of separate, independent objects. Galaxies are not isolated islands floating in empty space, but nodes in a vast network of filaments and flows that connect them to the larger cosmic web. Stars are not solitary beacons, but participants in complex ecosystems of gas, dust, and radiation that span entire galaxies. Even planets like Earth are intimately connected to cosmic processes through the chemical elements that make up their rocky surfaces and the energy flows that drive their atmospheric and geological evolution. The recognition of these deep interconnections has profound implications for how we understand our own place in the cosmic scheme. We are not separate from the universe, but expressions of it, temporary arrangements of atoms and energy that have emerged from billions of years of cosmic evolution. The calcium in our bones was forged in the cores of massive stars. The iron in our blood was scattered through space by ancient supernovae, and the water that makes up most of our bodies condensed from primordial hydrogen in the cold depths of interstellar space. This cosmic perspective transforms our understanding of what it means to be alive and conscious in this universe. We are not outside observers looking in at cosmic processes, but participants in them, conscious manifestations of the same physical laws that govern the formation of galaxies and the evolution of stars. Our thoughts and dreams emerge from neural networks that operate according to the same electromagnetic forces that light up nebulae and power the aurora. Our heartbeats follow rhythms that echo the pulsations of variable stars and the orbital dances of binary systems. The study of cosmic structure also reveals the universe as a place of extraordinary beauty and elegance, where mathematical principles manifest themselves in patterns of almost artistic sophistication. The spiral arms of galaxies trace logarithmic curves that appear throughout nature, from nautilus shells to weather systems. The clustering patterns of galaxy clusters follow statistical distributions that connect cosmic architecture to the deepest principles of probability and information theory. Even the vast empty voids between cosmic filaments have their own geometric beauty, creating negative spaces that are as important to the overall pattern as the bright filaments themselves. This aesthetic dimension of cosmic structure suggests deep connections between mathematical beauty and physical reality, hinting that the universe might be organized according to principles that transcend mere mechanical causation. The fact that the same mathematical relationships appear at scales ranging from quantum mechanics to cosmic structure suggests an underlying unity in the laws of nature that we're only beginning to appreciate. It's as if the universe is written in a mathematical language whose grammar and vocabulary we're gradually learning to decipher. The future of cosmic structure research promises discoveries that will continue to revolutionize our understanding of the universe's architecture. Next generation surveys will map billions of galaxies with unprecedented precision, revealing the cosmic web in exquisite detail and potentially uncovering new types of structures that we haven't yet imagined. These observations might reveal signatures of exotic physics operating on cosmic scales, from extra dimensions to modifications of general relativity to entirely new forms of matter and energy. The integration of different observational approaches will provide increasingly complete pictures of cosmic structure. Optical surveys that map the positions of galaxies will be combined with radio observations that trace the distribution of neutral hydrogen, X ray measurements that reveal hot gas in galaxy clusters, and gravitational wave detections that probe the mergers of massive objects throughout cosmic history. Each wavelength and messenger particle provides a different perspective on the same underlying structures, like viewing a sculpture from multiple angles to understand its full three-dimensional form. Machine learning and artificial intelligence will play increasingly important roles in analyzing the vast datasets generated by these surveys. Pattern recognition algorithms will search for subtle correlations and structures that human researchers might never notice, potentially revealing new aspects of cosmic architecture that challenge our current theoretical understanding. The universe will become a big data problem of unprecedented scale and complexity, requiring new computational approaches that push the boundaries of what's possible with even the most advanced computer systems. As we stand on the threshold of these new discoveries, it's worth pausing to appreciate how far we've come in our understanding of cosmic shape and structure. In just a few centuries, we've progressed from thinking of the Milky Way as the entire universe to mapping the three-dimensional architecture of billions of galaxies, spanning tens of billions of light years. We've discovered that most of the universe consists of mysterious dark components that we can detect only through their gravitational effects, and we've learned that space itself is expanding at an accelerating rate, driven by an unknown form of energy. Yet, for all our progress, the universe continues to surprise us with new mysteries and unexpected discoveries. Each answer we uncover seems to reveal new questions. Each measurement we make opens up new possibilities for exploration and understanding. The cosmic web we've mapped so carefully might be just the visible manifestation of even more complex structures operating in higher dimensions or at scales we haven't yet learned to observe. This ongoing dance between discovery and mystery is perhaps the most beautiful aspect of our quest to understand cosmic shape. We're engaged in a conversation with the universe itself, asking questions through our observations and receiving answers that often lead to even more profound questions. It's a dialogue that has been ongoing for as long as humans have looked up at the night sky and wondered about their place in the grand scheme of things, and it's a conversation that shows no signs of ending anytime soon. The shape of the universe, in all its complexity and beauty, serves as both our greatest scientific challenge and our most profound source of wonder. It reminds us that we live in a cosmos far stranger and more magnificent than our ancestors could have imagined, yet also more intimately connected to our own existence than we might have thought possible. Every breath we take, every heartbeat, every thought that crosses our minds occurs within the vast geometric framework that encompasses all of existence, making us not just observers of cosmic architecture, but active participants in its ongoing evolution and self discovery. As we draw near to the end of our gentle cosmic journey, it's worth reflecting on the extraordinary tapestry we've woven together tonight. We've drifted through concepts that stretch the very limits of human imagination, from the quantum foam that might bubble at the smallest scales to the vast cosmic web that spans billions of light years. We've contemplated universes that curve back on themselves like cosmic donuts, explored the possibility that consciousness itself might play a role in shaping reality, and marveled at the mathematical elegance that seems to underlie all of existence. The shape of the universe, as we've discovered, is far more than a simple geometric question. It's intimately connected to the deepest mysteries of physics, from the nature of dark matter and dark energy to the quantum mechanical foundations of reality itself. It touches on philosophical questions about the role of observation in determining what exists, and it opens up possibilities for future discoveries that might revolutionize our understanding of space, time, and consciousness. Perhaps most remarkably, our quest to understand cosmic geometry has revealed that we are not separate observers looking in at the universe from the outside, but integral participants in its ongoing evolution. The atoms that make up our bodies were forged in stellar cores. The elements that fuel our thoughts were scattered by ancient supernovae, and the very space through which our planet moves carries within it the echoes of cosmic inflation and the whispers of quantum fluctuations from the universe's first moments. This cosmic perspective transforms not just how we understand the universe, but how we understand ourselves. We are expressions of cosmic geometry, conscious manifestations of the same mathematical principles that govern the motion of galaxies and the behavior of subatomic particles. In seeking to understand the shape of space, we are ultimately exploring the deepest aspects of our own nature and our place in the grand cosmic symphony. The tools we've developed for probing these mysteries, from gravitational wave detectors to supercomputer simulations, represent some of humanity's greatest technological achievements. Yet they also remind us of our limitations, of the vast scales and subtle effects we're trying to measure, and of how much we still don't know about the cosmos we inhabit. As we look toward the future, with new telescopes coming online and theoretical frameworks continuing to evolve, we can expect even more surprises and revelations about the nature of cosmic architecture. The universe has a delightful habit of exceeding our expectations, revealing new layers of complexity and beauty just when we think we're beginning to understand its basic structure. But perhaps the most beautiful aspect of our cosmic quest is how it connects us to something larger than ourselves, while simultaneously revealing the profound mystery that lies at the heart of existence. Well, no matter how precisely we measure the curvature of space, or how elegantly we describe the mathematics of cosmic evolution, the universe retains an essential mystery that keeps us humble and filled with wonder. So as you drift off to sleep tonight, carried by the gentle rhythm of cosmic expansion and cradled by the invisible geometry of space-time itself, remember that you are part of something magnificent and mysterious. The same forces that sculpt galaxies and bend light around massive objects flow through every atom of your being. The same quantum fields that fluctuate in the vacuum of space participate in the neural processes that generate your thoughts and dreams. You are both infinitesimally small in the context of cosmic scales and profoundly significant as a conscious witness to the universe's ongoing attempt to understand itself. In your curiosity about cosmic shape, the cosmos achieves something remarkable. It becomes aware of its own architecture, capable of contemplating its own infinite mystery and beauty. Sweet dreams, fellow traveler in this cosmic dance, and may your rest be filled with the gentle whispers of space time itself, carrying you softly through the night on currents of dark energy, while quantum possibilities shimmer like distant stars in the darkness of your peaceful slumber.